Welcome students to Chemistry 317. That's quantitative analysis. I hope you had a great summer, and I'm sorry we have to kick off the semester remote, but anyhow, we'll see if you like this format this semester, and if not, we will try to tweak it. Anyhow, my name is Dr. Christy Proctor, and I have been here at CSU Pueblo for a long time. A little bit more of that to come. But just want to welcome you to what I hope will be one of your favorite chemistry major courses. So before we jump into course material, I think it's really important that you get an understanding of who I am, and I hope to get to know each of you better. Learning is a process, and we are all individuals, and we all learn a little differently, and so I think it's just kind of important to know a little bit about the people that you work with. So anyhow, to start with, I earned my PhD in Fort Collins, CSU Fort Collins, in 1989, long time ago. Time really flies quickly. Just a piece of advice in life, that adage about time going by faster the older you get, it is really true. Anyhow, so my PhD is in analytical chemistry, and thus that's why I'm teaching quantitative analysis, and I like to teach instrumental analysis as well. I am a native of Pueblo, and I actually earned my undergraduate bachelor's degree at what was University of Southern Colorado in actually that should be 1984. Anyhow, two majors, chemistry and biology. I thought I was going to go pre-med and changed my mind. I fell in love with math, and chemistry was an application of math, and that's how I ended up deciding to get a PhD in chemistry. Anyhow, my academic career, once I got my PhD, I didn't intend to return to Pueblo, but things happened, and I did return to Colorado State University of Pueblo directly out of my PhD program. Never intended to spend my whole career here, but look what happened. I have spent 17 years in different administrative positions along the way. I have loved my career, by the way. I like to be challenged. I like to learn new things. I like to do different jobs, and I haven't been disappointed. I was the department chair of chemistry for 6 years and actually guided the renovation of the building, which was a ton of fun, a lot of work. I also was assistant provost, dean of the College of Science and Math. I served on the board of governors. I was dean of graduate studies and research. Most recently, I was one of Dr. Motte's presidential fellows. And because I like to do different things and expand my horizons, I also have gone up to the Air Force Academy and been a distinguished visiting professor up there 3 times, including this past year. So anyhow, I have a very diverse background. I like to do different things, and if you're curious about any of these aspects of my career, and if you're thinking about maybe going on to a graduate degree or whatever, I'd be very happy to sit down and talk with you about your career aspirations. So a little bit about who I am. I am a Colorado native from Pueblo. Graduated from East High School many years ago, 1980. I was valedictorian. So yes, I am one of those overachiever people. I'm the youngest of 4 girls, so I think psychologists say that, you know, you're either a deviant or you're an overachiever, and so I'm the latter. My older sisters, we all kind of went into the STEM fields, which is kind of cool. But my sister Debbie is a project manager on campus at CSUP for the student fee funded projects. You may see her around. This is Debbie here. My sister Carla is a retired pediatrician. She's here in the picture. Some of you may have had her as your doctor, possibly. My sister Pam got her BS degree in chemistry here at CSUP, and she went on to a 40-year career at Sandia Labs. She's standing here with her daughter, my niece Nicole. This is her wedding from years ago, a couple years ago. My mother is still alive. She is 89 years old. We are blessed to have her still in our lives. And as you might anticipate, we are protecting her at all costs against COVID. So please stay healthy and clean and don't expose me to COVID so I can go visit my mother. Anyway, my other niece is right here. She graduated from CSUP with a psychology degree last year. She's on to gainful employment in Colorado Springs. And anyhow, this is me. You will meet me on Thursday if you don't already know who I am. So that's my family, my siblings. Really proud of my sisters and what they've all done. We are the product of my parents. My dad, Carl, was a land surveyor, had an associate's degree. So that's kind of where the love of math came from. He very tragically died young in life in 1985. Everybody has little things in our lives that we have to overcome, and that was a big one for me. My mom is, as I mentioned, still alive. She was an elementary school teacher with an associate's degree. What I like to do when I'm not teaching chemistry, I like to be outside. I like to play. I like to compete, friendly of course. So I like golf, tennis, hiking. I love Colorado, being in the mountains. I especially like just going out for a nice walk. You'll see one of my passions down here is my poodle Annie. She's 13 years old. You'll likely see her around campus and in my office. I like to bring her. She likes to come. She's very well behaved, so hopefully you'll have a chance to say hi to her at some point. Other things, I like photography. I like going places. I like traveling, and I'm kind of a kid at heart, so I like most games of various sorts. Other passions of mine, I have turned my research area of interest after all my administrative positions into chemical education. And so I'm creating Chemistry Tales videos with Annie in a studio, and you may actually get to use some of these resources on my YouTube channel. Chemistry Tales. Do you see the play on words here? So the poodle tail is my signature trademark for my videos. Anyhow, so other things that are fun in my life, I have a Corvette. I love Pixar movies. Cars was one of my favorites, so I nicknamed my Corvette Lightning McQueen. Other things I like to do, my friends and family were big Bronco fans. So here's my 2 seconds of fame. A few years ago, before the Broncos won the Super Bowl, they played the Patriots. So here is Tom Brady. And in row 2, 35-yard line, behind the Bronco bench, here I'm sitting, rooting against the Patriots. Here's my best friend Jill. So I'm part of NFL film, so there's my claim to fame for life. Okay, so important information. I actually prefer to be called either Dr. Proctor or Dr. P. Anything's good except that everybody's got a pet peeve. Mine is being called Mrs. Proctor. I don't know why, but I would just prefer if you would use one of the other titles for me. Where you can find me, my office is in the 4th floor of the chemistry building, room 419. It's right next to the graduate student office, if you know where that is. My phone extension is 2507. The extension for the chemistry department is 2574. Chemistry does not have an administrative assistant, so that latter number is going to ring through to the dean's office. Somebody should always be picking up that phone and can hopefully help you. The best way to get a hold of me and get information to me is my email. I check it frequently, so just always make sure you let me know if for some reason you're going to be late to class or you're going to miss class. Usually there's no problem with that, but just make sure you're always in clear communication with me. Office hours are Monday, Wednesday, Friday, 11:30 to 1. If that doesn't work, just let me know when you're available, and I'm sure we can figure out a time to get together. If you prefer face-to-face, if you would prefer to Zoom, we can do that too. Okay, so the course syllabus is on Blackboard, and so that's going to give you an overview of the material we'll be covering every week, the requirements for class, that kind of thing, and I'll talk about that a little later as well. But real quick, just some strategies for success. This is true for this class, and it's probably true for all your classes. So you're paying a lot of money to, hire your professors. So you really should make use of class time. Come to class and attend and participate, ask questions. There truly are no stupid questions. If you have a question about something, it's likely somebody else does too. And the critical thing to learning is just to address any fuzzy areas so that you get a solid foundation and can move on and build your knowledge. So especially in chemistry. So anyway, please come to class and please ask questions and be prepared. So read the chapters and begin working problems before we address the material in lecture. That way you're familiar with terms and you're not just hurriedly writing stuff down because, oh, it's the first time I've heard that word, so I better write it down. If you've already been exposed to it, then you can be listening with a higher level of anticipation. So you learn a lot more that way. Make sure that you learn how to take good class notes and organize class notes, because that is a really good way to study for exams, especially when we work problems. And then it's always a good rule of thumb to look at your notes once you've left class, and while stuff is kind of fresh in your head, that way if anything in your notes isn't really clear, that's the kind of thing you want to drop by my office hours and get some help with and say, hey, I think I missed something here, I missed a step, can you fill in the blanks. Another huge thing in chemistry classes especially is do not get behind. Chemistry is a discipline that builds. Once we learn something, we use it as a building block to understand the stuff that's coming up. So once you get behind, it's really hard to recover. So try to keep up with course material when we're covering things. And then the other critical thing is working homework problems. Because in chemistry, it's an application science. So we learn about the theory and knowledge of stuff, but where it's useful is when we apply it in understanding data and measurements and that kind of thing. So I'll explain later as to how we'll do homework this semester, but completing your homework is the critical step to understanding the material for this class and many other chemistry classes. So the required materials for this semester, your textbook is Quantitative Chemical Analysis. It's a 10th edition. The author is Daniel Harris. The publisher is Freeman and Company. And this is a very newly minted edition of the text. Also available to you and on the Blackboard website is an open educational resource book, Analytical Chemistry, put out by an author by the name of David Harvey. I put it there mostly as supplementary to your primary text. You can access that text on LibreText, and there's the website for it. So it's a great resource. The homework you're going to be doing is tied to the Harris textbook. And it's specifically tied to the 10th edition. If you want to save money and find an older edition of Harris, that could be okay. Just know that the problem numbers are going to tie to the 10th edition and the chapter names and numbers and that kind of thing. So there's some changes from the 9th edition. So once again, if you don't want any problems, get the 10th edition. If you want to save some money and get the 9th edition, you probably can. There's a pretty good deal with the homework and the ebook that you can get from Sapling Learning. So the Blackboard website for our course is listed there. And then the Sapling Online homework is required. So you will have to go to the Sapling website, create an account, find our course at Colorado State University Pueblo, enroll, register, and pay. Once again, you can choose a package that has the ebook and the online homework. You can do that through our bookstore, but I think it's more expensive that way. For the laboratory part of the class, which is a separate class, you are going to have a bound notebook, safety goggles. For both lecture and lab, you need an approved scientific calculator. I don't care if it's programmable or not, because at this level you probably need a calculator that's got some functions to it. And then once again, as an optional part of the course, you could get the solutions manual for the problems that are in the textbook for the 10th edition Harris Analytical Chemistry text. Okay, so critical things in the syllabus. Where does your course grade come from? We are going to take 3 in-class exams during the semester. Those exams are going to be 200 points each, so those will contribute 600 points. The online homework is required. I will have deadlines 3 different times during the semester right before we take an exam. So I'm kind of giving you a little leeway to monitor yourself to make sure you're getting your chapter homework completed as we're going through the different chapters and not waiting till the last minute. So you need to be very adult about your time management practices and make sure that you're keeping up. So the online homework will contribute 3 at 100 points each, so 300 points in the course, which is 25%. And then we will take the standardized the Standardized American Chemical Society final exam for analytical chemistry. It too is going to be worth 25% of your grade. And just a note real quick, because of COVID and the fact that once you leave for Thanksgiving, you're not coming back, I can only give this exam to you in person. So we will be taking it the Thursday before Thanksgiving break. So we're going to have to get a little ahead of the material so that you're prepared to take the final a little early this semester. Okay, so to kick off our class this semester, Analytical Chemistry. So Analytical Chemistry is a subdivision of the chemistry discipline. If you haven't recognized this already, I can't imagine that you haven't, but the field of chemistry is kind of subdivided into 5 different subdisciplines. Analytical is one, the others are organic, inorganic, physical, and biochemistry. So what is analytical chemistry? Well, analytical chemistry is involved with the analysis of samples, matter. If you'll remember the definition of chemistry, chemistry is the study of matter. Okay, so matter is, makes up everything in the world, right? And in studying matter, we make measurements of the chemical and physical properties and the reactivity of matter, and we interpret the data and the results from those measurements. So kind of in a nutshell, analytical chemistry is that corner of chemistry involved with this analysis. Taking a sample and figuring out what chemical compounds are present and figuring out what concentration of each of those compounds is present. So the field involves a lot of the sophisticated instrumentation that you'll come to use if you're a synthetic chemist and you're producing a product and you want to identify its purity and you want to affirm its chemical structure. You're going to turn to instrumental techniques to do that, or there are simpler methods sometimes that we can use to just determine the concentration of species, like an acid-base titration. So analytical chemistry is the study of all of these various techniques. It's the development of those techniques, it's the validation of those techniques, and the application of those techniques. So some of the tools that we use to make our measurements, the basis of measurements has to deal with following something that we call an analytical signal. So the techniques or the tools that we use are going to reflect or respond to an analytical signal, and the different signals define the different methods or the instrumental tools. So they can go from the very simple to the very complex. So we can follow the volume of a solution as our analytical signal. The instrument that we use for those techniques is a burette, a Class A burette. A Class A burette costs about $50. So, it's not $2, but it's also not millions of dollars. So that is a very cost-effective technique. So anytime we carry out a titration, that analysis method is pretty cost-effective. And keep in mind, industries, chemical industries, the bottom line is profit. So if you can carry out an analysis that gives you the answers you need cheaply, that is going to be what you're going to do. So even though there's all these incredibly impressive instrumental methods out there, if you can get the information you need cheaply, that's what you're going to do. On the other end of the spectrum, if one uses nuclear spin states as our analytical signal, the associated instrument is an NMR. Nuclear magnetic resonance spectrometer. Depending on the magnetic field strength, those instruments can cost in excess of $1 million. So, the information you can get from an NMR spectrum, you can piece together the structure of a compound, which is a very powerful thing to do. But that too is just one of many of the tools that an analytical chemist can use to derive the information that you're trying to figure out about a sample. Okay, so one of the first things that is addressed in the introductory chapter in your textbook is what we mean by the analytical process. So as a chemist that needs to find out information about a sample, there's basic steps that we go through to get the answers that we need. So the first step is to figure out what it is we need to know. That is formulating the question. So the specific question to be answered by the chemical measurements. I need to know the concentration of iron and cobalt, which we believe to be macroscopic components in the sample. Okay, so that's what we're going to try to figure out about our sample and a little bit about the parameters of our measurements. So once we know what we're trying to do, formulating the question, now we need to select the analytical procedures and the techniques that are going to give us the needed information. Okay, so selecting the analytical procedures. So how do we go about that? Well, we typically go to the primary literature, see what's published about the analysis of this particular kind of sample for these particular kinds of compounds in these concentration ranges, and we can see what other people have used. We can also go to the Environmental Protection Agency, which has its standard methods for very specific analyses for very specific compounds in very specific samples. Like you can figure out what the standard method is to determine the content of calcium in oysters. So those are the kinds of things you can figure out from the standard methods. The next step is sampling. Okay, so we're going to analyze a sample. So how do we go about getting that sample? So acquiring the sample and making sure it's representative of the big entity from which we're drawing it. So there's a lot of detail sometimes that has to go into the sampling methods. If you think about river water, what time of day, what time of year, is it during runoff, how many feet from the shore, how deep, you know, all kinds of details with sampling. The next step is sample preparation. Once you have the sample, how do you get it ready for the analysis? So this is where we convert to form a suitable analysis. So our analyte is the substance of interest in our sample, and everything else around it is the matrix. And so sometimes there's an interfering relationship between those compounds. So sometimes you have to remove interfering compounds out of the sample. Other times it's easy, but sample preparation can be a big step in the process. Analysis. So once we've cleaned up the sample and we know that our analysis method is going to respond to the species of interest in our sample, now we perform the measurement. Okay, and we typically do so. We never do a measurement once. We oftentimes do it at least 3 times, if not more, because of something called standard deviation in replicate analyses. We want to have good precision, and so that means we're going to have to do things more than once. Once we have data, then we have to interpret that data and report it. So that's the next step, and that's very important. We need to understand statistics. We need to understand relevance. We need to understand the figures of merit of the instrument. So those are critical things. And then finally, once we've gathered the data and the information, then we typically draw conclusions about our analysis and get the final answers that we initially set out to obtain in step 1 when we formulated the question. So along the way with the analytical process, there's specific terms that we use over and over and over in this class. So you should be familiar with these. Your book will give you a definition. You know, I just want you to have a working knowledge so that if the terms are used in a question, you know what we're talking about. So a qualitative analysis is going to tell us what chemical constituents there are in a sample. It could be an ion, it could be a molecular compound, it could be a colloidal component. So it's just what is in the sample. Quantitative analysis, on the other hand, is going to tell us how much of specific species, chemical species, are present in the sample. The analyte is the species of interest in the sample. So when we conduct an analysis, that is the thing we're looking for. So when I said we were wanting to determine the calcium in oysters, okay, our analyte is calcium. The matrix is everything in the sample that is not your analyte. So it's everything outside of the analyte species itself. Okay, the matrix is important because it can interfere with your analysis. So like I said, sometimes you have to remove interfering compounds. Sometimes you have to do a sample separation to get your analyte species by itself when you make the chemical measurement. So the matrix is very important in the process of analyzing a sample. The methods that we use are kind of classified according to being what we call wet chemical techniques, and those specifically are gravimetric analysis, where we measure on the basis of mass using a balance, and volumetric analysis, where we do things like carry out titrations and measure volume. Those are simple methods, but they can be incredibly accurate and precise. So they are used a lot, even though they seem simple. Sometimes simple is the best thing you can do. Once again, they tend to be inexpensive to do. So a lot of chemical industries use simple methods. Instrumental methods are those using instrumentation, which are sophisticated instruments. This is NMR, FTIR, mass spectrometry, all of those kind of instruments that in our chemistry major, we have a standalone instrumental analysis class. And so you're going to learn about those techniques in depth in Chemistry 419. We will pay a little homage to those techniques in this class, but in this class we're a little bit more focused on the wet chemical methods and electrochemical methods. Terminology, we speak of analysis of samples, okay? And when we're talking about the measurements we're making of our analyte species, that is referred to as a determination. So we are going to do an analysis of oysters for the determination of calcium. So you see the distinction. Analytical signal is the thing that we're going to measure about our analyte species. That's what we're going to follow. And it's going to be indicative of how much of our sample is present, how much of our analyte species is present. Once again, the different methods of analysis, the analytical signals that we're following. So the wet chemical methods, we're measuring volume. If we're doing gravimetry, it's mass. If we're doing spectroscopy, we're measuring interaction of light with matter, so we're following some form of radiation. Electrochemical methods, we're following electrical analytical signals. So hopefully you can kind of get a sense of the distinction. And finally, just a pet peeve thing. So a machine is something that has gears and a lot of physical moving parts. Instruments are very sophisticated, very delicate, and oftentimes have either no moving parts or very, very few. So analytical chemists are very touchy about these terms. So don't refer to an FTIR or an NMR as a machine, because that, you know, it's just a completely different animal. So these are some of the terms that you're going to hear over and over this semester, so just try to become familiar with them. Okay, so moving on to chapter 1, chemical measurements. Okay, analytical chemistry is all about measurements of samples. So whenever we make measurements, we are going to have to use appropriate units. So remember, System International gives us the basic units for mass and distance. Mass is in kilograms, distance is the meter, time is in seconds, etc. So the 7 base SI units. From those we have derived SI units. So energy, force, all of those kinds of terms are what we call the derived SI units. When we use units, we typically work within the metric system. So these are the powers of 10 that get us into the right range of numbers. If we're dealing on the numbers of atoms or molecules or ions, those are huge numbers. So we need the huge metric prefixes, giga, etc. If we're dealing with very small measurements, the diameter of an atom, we're working down at the picometer or the angstrom, that's 10⁻10 meter scale. So we need to be able to use the appropriate range numerically using the metric system. we need to be able to convert different units. So unfortunately, most of us grew up with the the English system, and we're accustomed to things like pounds rather than grams, and feet rather than meters or centimeters. So we need to be able to convert between units. A lot of chemistry, chemical reactions, etc. Our chemical species have to be mobile so that they can crash into each other and undergo reactions. And so most chemistry is done in either the solution phase or gaseous phase. And along those lines, it's important that we are aware of the different concentration units. So we need to know the distinction between molarity, molality, weight percent, volume percent, and then if we're dealing with super low concentrations, trace quantities of analytes, we need to understand the units of parts per million, billion, and trillion. We need to review stoichiometry in doing analytical chemistry. Once again, because we deal with lots of solutions. Remind ourselves of the dilution equation, because we have a fixed number of moles and we're just simply putting that number of moles into either a bigger or smaller volume. And finally, you're going to be doing a lot of titrations, and so you need to be prepared to work lots of problems in which we're relating the moles of the titrant and the analyte and the stoichiometry involved, the concentration and the volume units. So quickly in review, table 1-1 out of the textbook gives you the base SI units, so length, mass, time, electrical current, temp, luminous intensity, amount of substance, etc. So just remember the SI units aren't necessarily kind of the most common units. So in mass, it's the kilogram, not the gram. In distance, it's the meter, not a millimeter, centimeter, etc. Current is in amperes, and the SI unit of temperature is the Kelvin. So just review those for future use in converting units. Okay, now we move on to derived SI units. Okay, so in doing analytical chemistry, we do a lot with spectroscopy and radiation. So remember, Hertz is the frequency of light. That's the inverse seconds, 1/seconds. Force is a Newton. That is a meter times kilogram over squared seconds. Pressure is the Pascal, which is a Newton over meter squared. Energy, important, really important, and different forms of energy, remember work and heat, etc. We measure with a joule, and that is a Newton times, it's a force times distance, right? Newton times meter. So that translates to meter squared times kilograms over second squared. Power is the watt, which is the energy per unit time. So it's the joule over the second. Quantity of electricity is the coulomb. That's the charge on a mole of electrons, and that's going to be the time multiplied by the current, amps. Electrical potential is the volt, and that is the watt over an amp. Okay, and electrical resistance is the ohm, and electrical capacitance is the farad. So we'll get into those latter three ones in the electrochemistry chapters, but just remind yourself of these derived SI units and be able to do some conversions. So table 1-3 gives you the metric prefixes. Some of these we don't use very much. The ones we are going to use the most, okay, are probably starting with giga, down to deca, and then actually we in analytical chemistry are used quite a bit down through here. So I would say for an exam you should be able to convert and use those metric prefixes effectively. Because when we get into trace analysis of constituents like you know, contaminants in water. You know, Dr. Kinney does his research on, you know, different pharmaceuticals and things that find their way into our water systems. And, you know, we actually have methods of analysis that allow us to measure down in these concentrations. So pretty tiny in terms of the nanograms per liter of sample, you know, in the parts per million, billion, trillion range. So anyway, so please be aware of these metric prefixes, the symbol, the corresponding power of 10, and then your homework is going to give you lots of practice in converting between metric units. Okay, so converting between different units. So you're just going to have to remind yourself of the different conversion factors here. We deal a lot in volume measurements. So remember, a liter is, remember, it's length times width times depth. So it's a cubic distance measurement. So 1 liter is the equivalent of 10 to the negative 3 cubic meters, which is huge. Okay. A milliliter, okay, is going to be, you know, 1,000 milliliters is the equivalent of 1 liter, correct? Because that's 10 to the negative 3. An angstrom is 10 negative 10 meters. An inch, the conversion I like to remember is there's 2.54 centimeters for every 1 inch. Okay, in terms of mass, English to metric, there are 454 grams in every 1 pound. Okay, so there's your mass conversion. We won't do a lot with dynes and newtons. Pressure, we're not going to deal a lot with gases. We'll deal a little bit, but if you do, here's your conversions between bars, atmospheres, and pascals, and torr, millimeters of mercury. Okay, energy, important especially in spectroscopy. Remember, energy is going to equal Planck's constant times frequency, or Planck's constant speed of light over wavelength. Okay. And then energy units in heat. So the calorie and the joule. So 1 calorie is equal to 4.184 joules. That one we use quite a bit. And then your temperature conversions are critical. Those are your more common ones. Your homework is going to give you plenty of practice converting between units. So if you need any help with the dimensional analysis and the setup of that, I'll be happy to help during office hours, or we can find a time to meet if those hours don't work for you. Your laboratory notebook is a very important tool that you have at your disposal, especially starting with this class. Your lab notebook, when you go to work and your company is potentially analyzing samples and the results can be used in forensics, could possibly send somebody to jail for life, or you're defending that you are upholding the Environmental Protection Agency and not contaminating waterways or something from things derived from your plant. Your lab notebook can become a legal record, and so it's vital that you understand how to organize the notebook, how to enter the information, etc. The simple rule of thumb is that somebody who doesn't know what you're doing should be able to pick up your lab notebook and understand what you're doing. So there should be an introduction where you've got the chemical reactions that are going on. You should have good illustrations or descriptions of the procedures and the steps you're using to carry out the experiment. You should have appropriate data tables where you enter your data with appropriate units. You should have your calculations following your data section, showing proper unit cancellation, etc., for where you get to your final derived values. As you'll learn when we go to lab, your entire grade's going to come from the accuracy and precision of your results. So you need to apply appropriate statistical interpretation of your data. And then finally, because it's a legal record, your entries have got to be in either blue or black ink, never pencil. And if you make an error, you just very neatly put a line through the erroneous information and then just keep trucking. So we'll talk about that further, but your lab notebook is really important. When we're in the lab, you're going to use a number of different instruments to make your measurements, and the accuracy of your measurements is going to depend exclusively on how well you maintain those instruments and whether you're following the appropriate use of those instruments. So the balance that records mass is critical to every single experiment, and so it is vital that you never spill anything in the balance, and in the event that you do, that it is cleaned appropriately, the materials are removed using appropriate procedures. So we'll talk more about that later. In the laboratory, you're going to be using what we call Class A glassware. These are manufactured to precision such that the thickness of the glass has to be consistent in order for that piece of glassware to either contain or deliver the precise volumes. So there's do's and don'ts of handling Class A glassware. If you put it in the drying oven, you warp the glass and ruin it. So you need to know what kind of glassware you're working with and when it's okay to put it in the drying oven and when it's not. Some of your experiments are going to deal with the isolation of a solid, usually an ionic compound or something like that. And so you need to learn to dry and filter those solid samples. And another tool at your disposal is learning to use Excel effectively for plotting data and for the statistical analysis of your data.